Build skills with experts anytime, anywhere. Get certified, get ahead. The world's largest selection of courses, affordable online courses and learning opportunities.
Installation and configuration fundamentals. Are you a systems administrator that needs to build and administer a Kubernetes cluster? If you do, then this is the course for you. First, we'll start off by introducing you to Kubernetes and the world of deploying container-based applications. We'll look closely at Kubernetes architecture, including cluster components and networking fundamentals. Then we'll look at how to build your own Kubernetes cluster, and we'll look at installation considerations such as deploying on-premises or deploying in the cloud. Together, we'll deploy clusters in both scenarios in some demonstrations. And we'll wrap it up with learning how we can interact with our cluster at the command line using kubectl and the basics of application and service deployments in Kubernetes. At the end of this course, you'll know how to build a Kubernetes cluster, both in local virtual machines and as a managed service with some of the major cloud providers. You'll learn what it takes to get an application up and running in your Kubernetes cluster. Before beginning this course, you should be familiar with the Linux operating system and administering it at the command line. You should have a firm understanding of TCP/IP-based networking and also understand the fundamental concepts of containers. I hope you'll join me on this journey to learn how to build a Kubernetes cluster and deploying container-based applications in Kubernetes. So let's start off with a course overview. We're going to kick it off with an introduction, and then we're going to look at the theory and the concepts behind Kubernetes that makes, well, Kubernetes in the module Exploring Kubernetes Architecture. Once we have that theory in our brains, we're going to move on into installing and configuring Kubernetes. We're going to look at both on-prem and cloud scenarios, doing a deep dive into how that really all pieces together in building our first cluster together. And then once we have that cluster up and running, I don't want to leave you hanging. We're going to go ahead and learn how to work with our Kubernetes cluster and do some basic operations like deploying a service and an application into our newly built Kubernetes cluster. All right, in this module, we're going to kick it off with a discussion to answer the question, what is Kubernetes? And once we know that, then we're going to move on to exploring the Kubernetes architecture. We're going to zoom in very closely on the cluster's components and also some basic networking fundamentals. Let's start our discussion with answering the question, what is a Kubernetes? At its core, Kubernetes is a container orchestrator. What this means is it's a Kubernetes job to start and stop container-based applications based on the requirements of the systems administrator or developer. Now, one of the key facets of Kubernetes is workload placement. If I need to deploy a container-based application into a cluster, how do I deploy it? On which servers does it physically live on? Does it need to be co-resident with other services or containers inside of the cluster? If that's the case, we can define that in our code that describes our application, and Kubernetes can manage that for us. Now, speaking of Kubernetes managing things for us, Kubernetes also provides an infrastructure abstraction. As a developer, if I need to deploy an application into production, I really don't want to have to care about which server it lives on or have to go configure a load balancer to send traffic to my application. That's all going to be handled for me under the hood by Kubernetes. One of the other core ideas behind Kubernetes is this concept called desired state. We can define what our applications or our services look like in code, and it's the job of Kubernetes to make sure that our system meets that defined desired state. And so perhaps our application or our system is composed of some collection of web application containers and database containers, maybe some middleware or even a caching tier. We can write the code that describes what our system looks like, hand it off to Kubernetes for deployment, and it's Kubernetes' job to make that happen, to make sure that our system is in that defined desired state. Let's look at some of the key benefits of using Kubernetes. And first off is speed of deployment. Kubernetes gives us the ability to deploy container-based applications very, very quickly. And what this enables us actually to do is to get code from a developer's workstation into production fast. And that gives us the ability to absorb change quickly. The speed of deployment really allows you to iterate quickly and get new versions of code out, enabling new key capabilities for your organization's applications. Next up is Kubernetes' ability to recover very quickly. When we define our system in code and we define that desired state, so perhaps a collection of web app containers, and something causes our system to no longer be in that desired state, so perhaps a container crashed or a server failed, well, it's Kubernetes' job to ensure that our application comes back to that defined desired state by deploying new containers supporting our applications, making sure that we have that collection of web app containers up, or really whatever resource it is that defines our application or our system's desired state. And then finally, Kubernetes allows us to hide infrastructure complexity in the cluster. And so things like storage, networking configuration, and workload placement are core functions of Kubernetes, and developers don't have to worry about these things when deploying container-based applications into Kubernetes. So now that we know what Kubernetes is and the benefits of Kubernetes, let's look at some of the basic operating principles behind Kubernetes. And first up is desired state or declarative configuration. This is where we define our application, or really our deployment's state in code. We define what we want to deploy, and Kubernetes makes that happen for us. It'll go and pull the specified container images and starts them up, and possibly even allocates load balancers and public IPs if that's what's defined in our deployment's code. We write the code describing the deployment. Kubernetes does the work to bring it online in the desired state. Next, controllers or control loops have the responsibility of constantly monitoring the running state of the system to make sure that the system is in that desired state. And if it's not, a controller will try to bring the system into the desired state. And so, for example, if we've defined that we want 3 web app containers online, it's Kubernetes' job, more specifically a controller's job, to ensure that 3 web app containers are online. A controller will start the 3 replicas up, and later, if one of those fails or goes offline, a controller will create a new web app container replacing the one that failed. Now, there are many different types of controllers available in Kubernetes for various scenarios, and we'll cover them throughout this series of courses. But the key concept here is controllers are what make changes to the system to ensure the desired state. Another core principle is the Kubernetes API. The Kubernetes API provides a collection of objects that we can use to build and define the systems that we want to deploy in code. The objects defined in our code define the desired state of our applications or the systems that we want to deploy in Kubernetes. The Kubernetes API is implemented and available via the API server. The API server is the central communication hub for information in a Kubernetes cluster. This is where we, as administrators and developers, interact with Kubernetes to deploy and manage workloads. And it's also where the components of a Kubernetes cluster interact with each other to understand the current state of the system and to make changes to that state if needed to ensure the desired state. So let's look more closely at the Kubernetes API. Behind the scenes, you'll find there are a collection of API objects. These objects are primitives that represent the state of the system. So things like pods, which represent a deployed container, or nodes, which represent servers that do work in your system. These API objects allow us to configure the state of the system. And we can do that both declaratively and imperatively, where declaratively, what we learned means we can describe the implementation that we want to have, or we can describe that deployment and how we want our system to look. Imperatively means we sat down at the command line and executed a sequence of commands to get the system to be in the state that we want it to be in. So as we continue along learning about the API server is a RESTful API that runs over HTTP or HTTPS using JSON. And this is going to be the sole way that we as administrators interact with our cluster. But it's also the only way that Kubernetes interacts with the cluster as well. There are other facets of the system that will be exchanging information, and all of that has to go through the API server. Now, when we're communicating to the API server and we're telling it to create things or to change objects into different configuration states, that information is serialized and then persisted into the cluster data store. Now let's look at some of those core primitives, the Kubernetes API objects. These are going to be the building blocks for our deployments inside of Kubernetes. And first up is pods. What pods are a single or a collection of containers that we deploy as a single unit. This essentially is our container-based application. Then we have controllers. These are the things that keep our system in the desired state. So things like replica sets and deployments are going to become core tools in our toolbox as we build deployments in Kubernetes. Now, services provide a persistent access point to the applications that we deploy in pods, because as things change under the hood and our pods get redeployed perhaps by our controllers as they come up and down, those things will be constantly changing. Well, it's the service's responsibility to provide a persistent access point to the applications provided by our pods. And finally, there's storage. Of course, we'll need to be able to store data somewhere, and Kubernetes gives us some storage objects so we can have persistent storage in our applications. Now, this certainly is not an exhaustive list of all of the API objects available in Kubernetes, but these are the key players, the core things that we'll build our deployments from. So let's look a little closer at each of these core API objects that we just introduced, and we're going to start the conversation with pods. What a pod is a construct that represents one or more containers inside of a Kubernetes cluster. What it really is those container-based applications or services that you need to deploy into your Kubernetes cluster or your production environment. From a Kubernetes standpoint, it's the most basic unit of work. In fact, it's the unit of scheduling. When we define a pod, we also can define some of the resources that it requires inside of the manifest that describes our deployment. It's up to Kubernetes to ensure that those resources are available and schedules that pod onto those resources in our cluster and brings our application up and running. Another key attribute of pods is that they're ephemeral. What this means is that no pod is ever redeployed. If I deploy an application as a pod based off of a container today, and that pod dies, if I go ahead and redeploy that pod again based off of that same container image, no state is maintained between those two deployments. Once that pod goes away, it never ever comes back. That new pod is going to be deployed and provide those services of that container-based application in that pod deployment. Another key attributes of pods is the atomicity of a pod. They're either there or they're not. Now, in a single container pod, this kind of makes sense. My pod's up and running. If the container dies, well, yeah, that pod's no longer available. In a multi-container pod, if I have more than one container deployed inside of a pod, if one of those containers dies, the entire pod becomes unavailable, and that pod is no longer providing the services that it should. Continuing the conversation about pods, what I want to introduce now is that it's Kubernetes' job to keep your pods up and running using controllers. But more specifically, it's about keeping your application or your deployments in the desired state. And so to do that, to make sure that things are in the desired state, Kubernetes tracks the state of a pod. Is our pod and the containers inside of that pod up and running? Now, of course, our pod could be up and running, but the applications inside of that pod could be throwing errors. So Kubernetes also tracks the health of a pod. Is the application inside the pod up and running? And so Kubernetes can check the health of an application running inside of a pod with probes. In our deployment code, we can define a probe to check the health of our applications. And so, for example, if we've deployed a web application, we could write a probe that checks a URL and tests to see if the application is responding in an appropriate way. And so if that probe fails, then Kubernetes can understand that and make the appropriate adjustments to that individual pod that might not be responding in a healthy way. And this could be deleting the pod and replacing it with a new one. We're going to look much more closely at pod internals and probes in an upcoming course. But for now, what I want you to understand is what they are and the role that they play inside of deploying applications in Kubernetes. We're going to look at them very closely later on. So now that we know what pods are and that they can come and go based on status and health, how does Kubernetes manage my pod state? What's the thing that makes sure that our pod is up, running, and healthy? Well, that's where controllers come in. A controller defines the desired state for your cluster and the applications deployed in it. It's the job of the controller to ensure that things stay in the desired state. Controllers are exposed to you as workload resource API objects and are most commonly used to create and manage pod-based applications deployed in Kubernetes. These API objects will create and configure the controllers needed to create and manage your pods for you, and they ensure your applications stay in the desired state. So for controllers to define and manage the desired state of applications deployed as pods, controllers monitor and respond to the state and health of pods deployed, ensuring the desired number of pods are up, running, and healthy in a cluster. And if the state or the health changes, the controller will respond accordingly, trying to make sure that the system stays in the desired state. The first controller that we're going to look at today is the replica set. You've heard me describe this scenario a couple of times so far in the course, where I want to have a collection of web application containers up and running in pods. Well, that's what a replica set models. It allows us to define the number of replicas for a particular pod that we want to have up and running at all times. And so if I want to have 3 pods of this particular web app running at all times, well, it's the replica set's job to make sure that those 3 pods are up and running at all times. If one of those pods becomes unavailable or unhealthy for whatever reason, it's Kubernetes' job to delete that failed pod and deploy a new pod with the hopes of that new pod returning the system back to the desired healthy state. When it comes to deploying applications in Kubernetes, you generally won't create replica sets directly. You will create deployments. On the creation of a deployment, it creates a replica set based on what's defined in the deployment. And the deployment manages the state of the replica set. So things like which container image to run and also the number of pods to create. But more interestingly, the deployment controller manages the transition between 2 replica sets. And a practical example of this is moving between 2 versions of an application. When we define our initial deployment, it creates a replica set. Let's say running version 1.1 of a container image for our application. We can use a deployment to control the transition to a new collection of pods, perhaps running version 1.2 of our application. A deployment controller controls the transition and even gives us the ability to roll back if needed. Deployments are core to the success of deploying applications in Kubernetes, and we'll look at them in more detail in this course and in much more detail in upcoming courses. Now, there are many more types of controllers available in Kubernetes, not just ones based on pods. In future courses, as we continue along in our Kubernetes journey, we'll look at things like nodes, services, and other controllers that provide value to our Kubernetes applications and infrastructure. So now that we've introduced the basic principles of Kubernetes, let's move on into exploring the Kubernetes cluster architecture and look at what a cluster is actually composed of. And so let's look at cluster components. The first cluster component is the control plane node. The control plane node implements the major control functions of a cluster. It coordinates cluster operations, monitoring, pod scheduling, and is the primary access point for cluster administration. Next up is the node, sometimes called the worker node. This is where our application pods actually run. The node has the responsibility of starting up pods and the containers supporting those pods. Nodes implement networking, ensuring the network reachability to the pods and services running on worker nodes. Each node in a cluster contributes to the compute capacity of the cluster, and clusters are generally composed of multiple nodes based on the scalability requirements of the workloads deployed. And finally, nodes can be either virtual or physical machines. The control plane node used to be called the master node. And so in some documentation and resources on the web, you will see the term master node used. The modern name for this is control plane node. I'm in the process of updating this series of courses and will update this to control plane node in each course, updating the videos, code samples, and demos. So if you get to a course that I haven't updated yet, you will see this referred to as the master node. This is conceptually the same as the control plane node and will be updated as soon as I can get to that course. Zooming in on the cluster's control plane node. The control plane node, which implements the major control functions of a cluster, is comprised of several components, and the first is the API server. The API server is the primary access point for cluster and administrative operations. This is essentially the communication hub of our Kubernetes cluster. Now, the API server itself is stateless, and so we need a place to be able to store the state of the system, and that's where the cluster store etcd comes in. This has the responsibility of persisting the state of our Kubernetes objects. Next is the scheduler. The scheduler tells Kubernetes which nodes to start pods on based on the pod's resource requirements and other attributes such as administrative policies. And then there's the controller manager. The controller manager has the job of implementing the lifecycle functions of the controllers that execute and monitor the state of Kubernetes objects such as pods. Basically, it has the responsibility of keeping things in the desired state. And we're also going to introduce kubectl here. Not really part of the control plane, but it's how we're going to interact with the API server for administrative functions. When we work with kubectl, it's going to interact with the API server for us to be able to retrieve information and also to make those changing operations to help get our system into the state that we want it to be in, such as deploying workloads. It's our primary administrative command line tool for operating our Kubernetes cluster. And now we're going to deal with this right now. I call it kubectl. You can call it kubecontrol, kubectl, whatever you want to do, but for this course, we're going to go with kubectl. Now, within the control plane node, let's look even closer at those individual control plane components that we just introduced. We're going to look at the API server, the cluster store etcd, the scheduler, and the controller manager. Now, the API server is central to the control of your cluster. It's core to all operations. All configuration changes pass through the API server. It's a very simple interface leveraging a RESTful API, exposing RESTful operations like get, push, post, and so on. Based on the operation that's going into the API server, it's the responsibility of the API server to validate that operation and persist that object state into the cluster data store, which is etcd. And as we've introduced, etcd is the cluster data store and is used to persist the state of those API objects as key value pairs. Next up is the scheduler. It's the job of the scheduler to watch the API server for unscheduled pods and then schedule those pods on nodes. When scheduling pods, the scheduler will evaluate the resources required by that pod in terms of things like CPU, memory, and storage requirements to ensure their availability when placing a pod on a specific node in our cluster. Further, the scheduler has the responsibility of respecting any constraints that we define administratively. And so perhaps you want to keep 2 pods on the same node at all times. That's called pod affinity. Or perhaps you want to do the opposite, where we want to ensure that 2 pods are never on the same node. That's called pod anti-infinity, and the scheduler will handle that for us. The scheduler is capable of scheduling pods based on many different other attributes, and we'll look at this more closely in an upcoming course. And then finally, the controller manager. It's the job of the controller manager to execute those controller loops. Those controller loops implement the lifecycle functions of pods and thus define the desired state of the system. It's the job of the controller manager to watch the current state of the system and update the API server to ensure that it's heading towards the desired state. The replica set API object is an example of a controller that we'll be working with a bunch in this course. This is the controller that is used to ensure that the correct number of pods or replicas are up and running in our deployments. And so it's the responsibility of the replica set controller to communicate to the API server changes in its desired state. And so this could be operations like creating new pods or deleting pods based on what the running state of the cluster is. And as we've introduced, there are many different other controllers available in Kubernetes, and we'll introduce more in this course and in upcoming courses as we continue our Kubernetes studies. Now that we've introduced the control plane node and its core components, let's take some time to look at what a node does in our cluster. A node is where our application pods run. The node starts up the pods and ensures that the containers in those pods are up and running. Nodes also implement networking to ensure the reachability of the pods running on the nodes in our cluster. We can have many nodes in our cluster based on the scalability requirements of the applications that we're deploying inside of Kubernetes, and nodes can consist of either physical or virtual machines. Now, within a node, there are some components that I want to introduce you to, and first up is the kubelet. The kubelet has the responsibility for starting up pods on the node. Then there's the kube proxy, which has the responsibility for pod networking and implementing our services abstraction on the node itself. And then there's the container runtime. This is the actual runtime environment for our containers. The container runtime has the responsibility of pulling the container image from our container registry and providing an execution environment for that container image and the pod abstraction. Now, both the kubelet and the kube proxy communicate directly with the API server, monitoring it for changes to the environment. And so as pods are scheduled to this individual node, the kubelet will monitor the API server for that information. And if it does have a scheduled pod, it'll start up the containers needed to support that pod on the node. Similarly, if there's a networking topology change that needs to be implemented, such as adding a newly created pod's IP to a service for load balancing, it's the responsibility of the kube proxy to monitor the API server and make that modification on the node. Let's look at those individual components of a node in more detail. We're going to look at the kubelet, the kube proxy, and the container runtime. Now, I do want to call out that all of these components actually will run on all of the nodes in the cluster. What this means is that even on the control plane node, these 3 services, the kubelet, the kube proxy, and the container runtime will run because there are going to be special purpose pods deployed onto the control plane node providing the control plane services. There's also going to be a kube proxy providing networking services and a container runtime as the execution environment for those pods on the control plane node. And so all of these services will exist on all nodes in our cluster. Looking more closely at the kubelet first, as we've discussed, it monitors the API server for changes. And so as pods are scheduled onto individual nodes, it's the kubelet that goes and asks the API server, hey, do you have any work for me? And the API server answers that question, yes or no. The kubelet is also responsible for pod lifecycle, meaning starting and stopping pods and its containers in reaction to those modifications or those state changes that are being watched on the API server. In addition to monitoring the API server for changes, it's also the responsibility of the kubelet to report on both node and pod state. So if a node is reachable and reports its status as ready, then it's available for scheduling of new pods in our cluster. The kubelets also have the responsibility of monitoring pod state. Is the pod up and running? That's all reported back to the API server via the kubelet. If there is a probe used for determining pod health, it's the responsibility of the kubelet to execute that probe. Now, the kubeproxy has the responsibility of all networking components for nodes, and it's most commonly implemented in IP tables. There are other modes for kubeproxy, but for this course, we're going to focus on IP tables. Kubeproxy has the responsibility of implementing that services abstraction that we introduced a little bit ago. And the kubeproxy is also responsible for routing traffic to pods. And so as application requests come into the cluster, kubeproxy has the responsibility of ensuring that those requests land on the correct pods executing on the nodes in our cluster. And the kubeproxy also has the responsibility of load balancing, making sure that traffic that's coming into multiple pods is distributed in an even fashion. The container runtime has the responsibility of downloading container images and starting and running containers. The container runtime in Kubernetes is wrapped up in what's called the Container Runtime Interface, or CRI. And this gives us the luxury of being able to swap out the container runtime, choosing from several different supported container runtimes. Out of the box, we're going to be using Containerd. This is the default container runtime in today's version of Kubernetes. There are many other container runtimes available to you, and you can use those in Kubernetes as long as they're CRI or Container Runtime Interface compliant. Before Kubernetes version 1.20, Docker was the container runtime used. In version 1.20, Docker was deprecated and will be removed in 1.22 or later. In practice, though, you can still use container images built with Docker in your Kubernetes cluster when using other container runtimes as long as they're CRI compliant. And in our cluster in this course, we'll be using Containerd. So now that we know the basic principles behind Kubernetes in terms of theory, and we looked at the components that a Kubernetes cluster is made of, let's see Kubernetes in action and see how this all pieces together. And we're going to start off with some pod operations. Let's say we have a cluster and it's composed of a control plane node and a couple of worker nodes. Using kubectl, we submit code to instruct Kubernetes to create a deployment. And in that deployment, we've defined that we want 3 replicas of our pod. That request is going to be submitted to the API server, and it's the responsibility of the API server to store that information persistently in etcd. With that, then, it's the responsibility of the controller manager to spin up those 3 requested replicas in that replica set. And so that's going to create those 3 pods. That request is then going to be submitted to the scheduler. The scheduler is then going to tell the API server that these pods need to be scheduled on nodes that it selects, and that scheduling information is persisted back to etcd. Which nodes do those pods get scheduled on? Well, that's dependent upon the resources requested in the pods and the resources available in the nodes in the cluster. The kubelets on the nodes will ask the API server, hey, do you have any work for me? And then it's going to start spinning up those pods that were requested by the replica set. Now everything is going along happy, and the controller manager is monitoring the state of the replicas, and everyone's reporting that they're in a desired state. But what happens if a node goes down? Well, that node is no longer reporting state, and the controller manager understands that we're now outside of the desired state in terms of the number of replicas required for our replica set. So the controller manager is going to submit for a new pod to be created and scheduled. And it's the responsibility of the scheduler to find a node to put that pod on. And so it schedules that new pod to be deployed on a node to bring our replica set back into compliance with the desired state of 3 replicas. Now, you might be wondering by looking at this picture, why didn't the scheduler schedule that pod onto the control plane node to maybe even out the workload a little bit between the control plane node and the worker nodes? Well, in the default configuration of Kubernetes, the scheduler taints the control plane node. And what this means is that the control plane node is only going to run pods that are system pods. And so in this case, the API server, etcd, the scheduler, and controller manager. Any user workload is going to be scheduled onto regular worker nodes in the cluster. We can certainly adjust the configuration of the control plane node to untaint the control plane node so that user pods can be started up on it, but that's usually only good for test labs, not good for production systems. Let's start this module off with discussing some installation considerations. What this boils down to is, where are you going to install Kubernetes? Where are you going to get this service from to deploy your applications? And first up is cloud. And here there are really two major use cases when deploying Kubernetes in the cloud. You can deploy infrastructure as a service virtual machines and deploy a Kubernetes cluster on top of that. With IaaS-based deployments, the networking, the hypervisor, and all of the infrastructure plumbing isn't something that you have to worry about. But you do have to worry about the operating system, patching it, and installing and maintaining Kubernetes itself as software on those virtual machines. And then there's PaaS offerings, or platform as a service offerings. Kubernetes is available as a managed service, and all of the big cloud providers provide this. And you can simply go ahead and consume Kubernetes as a service. You don't have to worry about any of the underlying infrastructure or redundancy. So one of the things that you do have to think about when you are going with a PaaS offering or a managed service offering of Kubernetes is you lose a little flexibility in the versioning and other features that are available inside of Kubernetes. So there's kind of a trade-off there. When you're building your own Kubernetes cluster using virtual machines in the cloud, well, you get to control exactly which version of Kubernetes that you install. But when you do that, you will take on more responsibility in administering the cluster when compared to a managed service or a PaaS offering. So another solution to getting Kubernetes is on-premises. You can install Kubernetes on bare metal physical machines, or you can get Kubernetes on-prem using virtual machines. And that seems to be a pretty common deployment scenario. And now that leaves us with one giant question. Which one do you choose? Well, that's really dependent on a couple of things. And what I like to think is that it's dependent a lot upon the skill set of the organization and the strategy of the organization. If you and your teams are cloud ready and you're already in a cloud and you're moving forward as fast as you can, well, yeah, it certainly makes sense to deploy in a cloud offering. Now, if you want to stay on-prem, well, that's fine too. Again, it goes to the skills and the strategy of the organization. Which one do you choose? Well, take all of these things into consideration when you're working out your installation considerations for Kubernetes. This course is about the installation and configuration of Kubernetes. So we're going to focus a lot on installing Kubernetes in virtual machines, but we are also going to look at some cloud scenarios together at the end of this module. Now, let's discuss some additional installation considerations that we want to take into account before we get started deploying Kubernetes. In an earlier module, we looked at pod networking and how pods need to communicate with each other. So we do have to take that into account before we install our cluster networking. Do we want to use an overlay network, or do we want to work with a network engineering team to make sure that we have the correct layer 2 and layer 3 connectivity between the pods and the nodes in our cluster? And we also want to ensure that there aren't any network IP range overlaps with what we're doing in our cluster and the rest of our network infrastructure. Then there's the question of scalability. Do we have enough nodes in our cluster with the appropriate amount of resources on each node in terms of CPU and memory to support the workloads that we want to deploy in Kubernetes? We also need to take into account that we have enough nodes in our cluster to support the workload in the event of a node failure. And then there's questions about high availability and disaster recovery. If you've noticed so far, we've discussed a single control plane node cluster. There's one control plane node doing all of the work and controlling everything in our cluster. That's certainly not a highly available solution. We'll learn in later courses in this series how we can take that control plane node and have replicas of the API server backed with multiple copies of etcd to provide redundancy for both the API server and the etcd data store. Additionally, we need to take into account for disaster recovery scenarios, ensure that we have backup and recovery of that etcd data store in the event of a catastrophic failure. All right, it's taken us a long time to get here, but it's time for our first demo together. In this demo, what we're going to do is we're going to install some packages together: Containerd, Kubelet, kubeadm, and kubectl. And with all those packages installed, we're going to look at some systemd units for some of these packages to understand how they operate with the underlying systemd system. All right, so here we are in VS Code, and let's get started with the process of installing the required packages to bootstrap our Kubernetes cluster. In VS Code here, what I'm going to do is highlight the code at the top, and I'll execute that code, and it's going to show the output at the bottom in our environment. So this way we're able to see both the code that I'm executing and the output at the same time. I've already gone ahead and deployed the 4 virtual machines that we discussed in the presentation portion of the course. So I have C1 CP1, C1 Node 1, 2, and 3 all up and running in my environment here. I also right now have an SSH connection open to C1 CP1, as you can see at the bottom here. And so let's go ahead and start the process of installing and configuring the proper software for our Kubernetes environment. The first thing that we'll need to do, and we're going to need to do this on every node in our cluster, is to make sure that our swap is disabled. And I've already actually done that for this virtual machine. And so here you can see if I do a swap off -A, I get no output because I've already disabled the swap file. And so let me go ahead and show you how I did that. I did that by editing the FS tab. Highlight this here, run that code at the bottom, and there we can see the contents of our FS tab. On the second line here, we can see that the swap is disabled because this line is commented out. And so what you'll want to do here is either delete that line, comment it out, save the file, and then reboot your system, and your swap will be disabled. And with that configuration complete, let's move forward into the installation and configuration of Containerd. Now, I want to call out that the Containerd installation right now is a little bit more complicated than I think it should be. And I expect that this process is going to become more streamlined as Containerd becomes kind of the centerpiece of the container runtimes for Kubernetes. And so what we're going to see here is we'll have to perform some extra steps to get this Containerd installation configured for us to use Kubernetes on top of it. And what I expect is that this is going to become more simple. And so I promise to keep this code up to date with the latest method, but this is the most current method for configuring and installing Containerd. And so let's walk through that process together. The first thing that we'll need to do is to load some modules. And with lines 28 and 29 here, I'm going to load both the overlay and the BRNet filter module. Now that's the runtime module that's right now in this configuration, but I also need to make sure that they're set on boot. And we can do that here on lines 31 through 34 with this here doc. And that's going to write the appropriate information into the mod-load.d directory in etcd. So we'll run that code there, and it'll create that file in the appropriate directory to ensure that these modules get loaded when the system reboots. We also need to configure some sysctl parameters. And again, we want to make sure that those persist across reboots. And so we'll grab this here doc here from lines 38 to 42, run that code, and it's going to write the appropriate sysctl parameters into /etc/sysctl.d in the file 99-kubernetes-cri.conf. With that file created, we can then apply that configuration with the code on line 46 here. So sudo sysctl space -- system. Now those configurations that were in that file are applied to the running system. With those configuration prerequisites complete, both the modules and the sysctl parameters set, it's now time to install Containerd. We'll make sure we have an up-to-date package list, and we can do that with the code on line 50 here, sudo apt-get update. Once we have the updated package list, we can install Containerd. And the code to do that is on line 51, sudo apt-get install -y Containerd. Run that code, and that's going to install Containerd for us on this system. Now with Containerd installed, we need to apply some configuration specific to Containerd, and we'll do that with the code here on line 55 and 56. First up, we'll create a directory for a Containerd configuration file to live in. And on line 55, we have mkdir-p/etc/containerd to make that directory. Now on line 56 here, we can use the Containerd command to generate a default configuration file. So there we see sudo containerd config default. That's going to generate a default configuration file. We're going to pipe that output into sudo t and write that output into /etc/containerd/config.toml. And inside that configuration file will be the configuration attributes for Containerd. We're pretty good with the defaults, except for one change. We need to change the cgroup driver of Containerd to systemd, which is required for our kubelet. And we'll look at how to configure the kubelet in the next demonstration a little bit later in the course. And what we're going to do here is grab the text here on lines 68 and 69. That's our cgroup driver configuration, and copy that into our clipboard, and then open up the config.toml file in Vim. And we're going to look for the string that we have on line 65 there that ends in containerd.runtimes.runc. And below that, we're going to paste in this text from 68 and 69 in that file. So let's go ahead and find that information in our config file. So jumping down to the bottom here, I'm going to look for containerd.runtimes.runc. Once I find that line, here we go. I'm going to add a new line and drop in that text that I copied from line 68 and 69. And so there we can see I added that configuration into the configuration file. And we're going to write that out and save it. With that written out, let's go ahead and restart containerd. And we can do that with sudo systemctl restart containerd to make that configuration change for containerd, part of the running configuration for containerd. With containerd installed and configured, now it's time to move forward and install the Kubernetes packages kubeadm, kubelet, and kubectl. And the first part of that process is to add Google's app repository GPG key to our system so that we can trust that repository. The next step then is to add the Kubernetes app repository to our local repositories list. And we can do that with the hero doc that's on lines 86 through 88. Run that code together, and that's going to configure that local app repository on our local system here. With that new repository added, we're going to want to update the package metadata information for our system so that we can get the package information from that newly added repository. We can do that with sudo apt-get update. Now let's take a peek at what's available to us to install from that new repository. And I want to look at the kubelet package just to see the different versions of the kubelet that are available. And I could do that with apt cache policy and then specifying the package name kubelet. I want to pipe that in ahead and limit that to 20 lines of output. In the output at the bottom here, we can see the different versions of the kubelet that are available as packages in the repository. So there we see 1.20.2-00, 1.20.1-00. And so those are all the different versions of the kubelet that are available to us to install. And what we're going to do here is we're going to pin our installation to a specific version. And we're going to install 1.20.1-00. And I have that set here as an environment variable on line 98. And what we'll do then is on line 99, we'll specify the exact version of the packages that we want to install. So there we see sudo apt-get install -y, and then the package name equals, and then we're referencing that environment variable that we just declared, version. We're going to repeat that pattern for kubeadm and then also kubectl, specifying the version for each, making sure that they're the same, all on 1.20.1-00. And the reason why I want to do that is because later on in this series of courses, we're going to run an upgrade to a newer version of Kubernetes. And so if you saw, there was 1.20.2 is available. So that way I have a version to upgrade to when we get to that course. Let's go ahead and run this code together to get the kubelet, kubeadm, and kubectl installed. Now with our packages installed, let's go ahead and mark all 4 packages with hold. And we can do that with sudo apt-mark hold, kubelet, kubeadm, kubectl, and containerd. And what that will do is prevent these packages from being updated when someone comes along and updates the system for security updates with apt. Now on lines 104 and 105 here, I have the code that'll allow you to install the latest and greatest version of Kubernetes. I held us back one version intentionally and also showed you how to pick a specific version. If you want to just install the latest version that's available, you can use the code that's on line 104 and 105. So now with the requisite packages installed, let's look at the systemd units for a couple of the services that were installed. And first up is the kubelet. I want to look at sudo systemctl status kubelet.service and look at the output that's generated for this particular systemd unit. And we can see something interesting here is that we see that the main process exited, code equals exited, status 255, failed with result, exit code. And we also see that the systemd unit's status is activating rather than active, which would mean that the service is up and running. What's happening right now is the kubelet's actually crash looping because there's no cluster configuration yet. We haven't told the kubelet to do anything specific. And so later on, when we get into the next portion of the course, we're going to learn how to bootstrap a cluster. And what that's going to do is write some information into a specific location that the kubelet's looking for. Well, that information is not available yet. And so the kubelet's going to be in what's called a crash loop, looking in that specific location for the configuration information that's generated by the bootstrapping process for our cluster. But we haven't done that yet. And so hang on to that thought right now. And a little bit later in the next demo, when we bootstrap the cluster, we're going to revisit this and see when the kubelet is up and running and healthy because our cluster has been bootstrapped. The other service that I want to look at is also containerd, just to make sure that that's in good shape before we move forward with our demonstrations. So sudo systemctl status containerd.service, run that code there. We can see it's active and running, so it's up and loaded and in a proper state. So let's break out of this output here. And one final step is just to make sure that both of these services are set to start up when the system starts up. We can do that with sudo systemctl enable kubelet.service. So let's go ahead and run that code. And we'll do the same sudo systemctl enable containerd.service to make sure that both of those services are set to start up when the system boots. So what we've done right now is we've installed the required packages to start building or bootstrapping our cluster, which you're going to learn about now in the next portion of the course.